Hello again, students of mathematical studies. In this video, we're going to answer the question about the two face cards in a three-card hand problem, and we're also going to answer the quarter problem finally pose something new. Well, for the three, you remember we had a tree diagram, and the tree diagram went face card, non-face card, face card, non-face card, non, etc., all the way down. We're going to look at those with some fractions right now. So here come some fraction bars, boom, 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 boom. Wow. And here are some denominators. So notice in our first round, there are 52 cards in the deck. Then there are going to be 51. Then there are going to be 50. So that's interesting. Let's bring some numerators in now. Let's deal with a couple of losing possibilities. One is going to be all face cards, that loses. Another one is going to be all non-face cards, those are going to lose. So we'll pop those in. All right. So you can see that the all face card route goes down from 12, 11, 10, because there were at first 12 face cards, so we got all face cards, then we drew 1 out of 11, then we drew 1 out of 10. The non-face cards, we drew 1 out of the 40, then 1 out of the 39, then 1 out of the 38. And that's why those numbers are coming in. The other numbers are a little bit more complicated, maybe, but take a moment to think about what they ought to be. If you want to try to produce this tree diagram for yourself, you can. And if you want to pause, go ahead and pause, because here come all of the other fractions. Magic. So now we got to take a look at which of these were the winning routes. And you may recall we could have gone face, face, non. We could have gone, let's do that. That's face, face, non. Or we could have gone non, face, non. No, wait. Non, face, face, right? Or we could have gone, is that it? No, there were three. There's face, non-face, face, face, non, non-face, face. That's it. So what we need to do is find these compound probabilities. You quotes right there, see? And they're real too, because there it is, compound probabilities. This is the other way around. It goes one way or the other, doesn't it? I mean, I'll figure it out later. Okay, so the odds of winning this game are going to be all this, or all this, or all this, for a grand total of this. Now I'm going to have to pause the video and do the math and tell you a little bit what that was. Cards were very fun. Let's get back to coins now and talk about the game that had 8 quarters being dropped. You're paying for the game that way, so it's $2 to play. And if it was 6, 7, or 8 of them were heads, then you win, and you win $5. So you're asked to work this out and say, is this game worth playing or not? And what you should have concluded is this game is not worth playing. This is a ripoff. Okay, you're going to lose the $2 way more often than you're going to win the $5, but so much more often, the odds of winning this game are very, very, very low. We're going to work out how to actually figure this out by using Pascal's triangle. You may remember Blaise Pascal's name coming up. He's one of these guys involved in inventing probability theory. Pascal did not discover his triangle, but he wrote a paper on it. And he explored so much about it that we've been calling it Pascal's triangle ever since. And it is a magnificent thing. So first, let's take a look at the general coin toss idea. And we can do a tree diagram and look at it this way. Now you might notice we've only got a few tosses going on here, and we've already run out of space. So for 8 coins, we have to come up with some other kind of framework. Well, to create this framework, let's suppose we just have 1 coin. 1 coin, and what we're going to do in this case is we're going to count the number of heads. That's what we're going to count. When you toss 1 coin, you can wind up with 0 heads, because it's tails, or 1 head. If you toss 2 coins, you can wind up with 0 heads, 1 head, or 2 heads. Let's consider the 2 coin thing for a moment. Here are the 4 possibilities. Toss 2 coins. Heads, 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 tails, tails, heads, and tails, tails. Notice that the 0 head possibility can only happen one way, and the 2 head possibility can only happen one way. But the 1 head possibility can happen one of 2 ways. So we have this. With 3 coins, there's one way for them to be no heads and one way for them to be all heads, but there's 2 ways, nope, wrong, three ways for them to be 1 head and 3 ways for them to be 2 heads. So our table is 1, 3, 3, 1. Now notice where this table goes to. Pascal's triangle starts here at 1, 1, goes to 1, 3, 3, 1. I'm going to scoot over so you can see Pascal's triangle a little better. 1, 3, 3, 1. Then it goes to 1, 4, 6, 4, 1. And you may notice a couple of things going on here. 11 is 11 to the first power. 121 is 11 squared. Yes, 1,331 is 11 cubed, and 14,641 is 11 to the fourth. This table is actually showing us the powers of 11. It's also showing us the coefficients that show up if you square x plus y, then you get x squared plus 2xy plus y squared. If you cube it, you get x cubed plus 3x squared y plus 3xy squared plus y cubed, etc., etc. This gives you the coefficients that happen when you raise binomials to different powers. So the Pascal's triangle is neat. It's got this binomial thing going on. If you follow this down, you'll notice that every number is the sum of the numbers above it. Yes, it is. Okay. We'll be back in a moment to discuss how this relates to the quarter game. Hi, we're back in front of a roaring fire. So with 8 coins, we're going to need 8 rows of Pascal's triangle. The rules of this game being 6, 7, or 8 heads, we pick a side of the triangle and we say, is this all heads over here or all heads over here? Let's do all heads over here. So we can see that if we have all heads, we win. If we have all but 1, we win. And if we have all but 2, we win. There are 8 quarters here. If all but 3, all of these other ones are losing. So this is the total number of ways to win out of how many trials. Now, when you add this up, you'll notice something else interesting about Pascal's triangle. What's 1 plus 1? Why, it's 2. What's 1 plus 2 plus 1? And what's 1 plus 3 plus 3 plus 1? And what's 1 plus 4 plus 6 plus 4 plus 1? Etc., etc. You notice that the rows of Pascal's triangle add up to the powers of 2. And so, the odds of winning this game are that percentage. Now that was the odds of winning this amount of money for an expected value of this amount. Way less than the $2 that it cost to play this game, and that's why the game is a ripoff. So what now? Now we're going to have an assignment. And the assignment is going to be this. Suppose we do the same game for $1.50. Okay? What would be an amount of money that makes the game an even bet? And that means if the prize is above that, it makes sense to play that game. If the prize is below that, it makes sense not to play that game. Interestingly, by the way, oftentimes you'll see something called a 50-50 raffle. They do these at events where they're trying to do a fundraiser or something. 50-50 raffle, from an economic perspective, is always a bad bet. Because what happens is, let's say they sell 100 tickets at $1 each. They collect $100. Well, the prize, because it's called 50-50, the prize is only going to be $50. And you're going to have a 1% chance of winning that $50, which means that your expected value is 1% of $50, which is 50 cents. And yet it costs $1 to buy the ticket. To pay $1 for 50 cents is to throw 50 cents away. And that's why 50-50 raffles are always for charity, because nobody buys that ticket thinking they're going to win. They buy that ticket thinking they're doing something nice. If you were doing it as a gambling thing, it would be an absolutely horrible game. So anyway, that's a 50-50 raffle, and that's some other stuff. Hope you've enjoyed this video. Enjoy working on the homework. Bye-bye.